briefly mention with algebra, symbolism is a key piece, or if not the piece, the language of algebra, and it's composed of two things: arithmetic numbers and literal numbers. Arithmetic numbers have an actual numerical value attached to them, right? So 1, 15, 200, a quarter, an eighth, decimal numbers. These are arithmetic numbers. They have a value. Literal numbers are also numbers that we just don't know the value yet. And the example that I was trying to demonstrate before we got kicked off was if we had a piece of bar stock and we had to cut this piece of bar stock into 3 equal pieces. We could measure this piece with calipers or with a tape measure and get an arithmetic number. But until we do that, until we measure it, and we don't know the value. But it doesn't mean it doesn't have a value. It's just we don't know it. So we assign a literal number to it. So in this case, let's just say that we assign here that this bar is x long. What does that actually mean? It means it has a value. It has a numerical value, an arithmetic number value. We just don't know what that is. Now, if I were to divide this bar up into 3 pieces, what is the length of this piece if I divide this bar up into 3 equal pieces? Well, because we don't know the value with an arithmetic number, we don't have an arithmetic number value here. We just have a literal number. We have to take that literal number and we have to form an algebraic expression that is true. So we would say that the length of this part is x divided by 3. Right? That would be true because this is 1/3 of the full length. So this is an algebraic expression. Okay, we have a combination of a literal number and an arithmetic number. Now, once we come to know the value of x, then we can now solve the rest of this expression. We now know the length of this part, because if this part were 12 inches long, we know that here, then this is going to be 12. If my eraser works, this is going to be 12 divided by 3, which we know is 4, right? So what this helps us do is find missing information by using literal numbers as placeholders until we can solve the equations. Let me just give you another example of how we would use these literal numbers and arithmetic numbers. So let's say that we have, this is the example I gave you in our handout. So if I have this piece of bar stock and I need to weld on an additional piece on this bar stock to achieve a certain length, right? I need to achieve a certain length, or I need the end result to be whatever length. So what I know is that in the example I gave you is that the length of this add-on piece is 0.8. The length of the existing rod, because the customer hasn't actually supplied it to us yet, let's say is unknown. So the length of the original piece is x long, and the length of the add-on piece is 0.8 long. So we know the overall length based on using literal numbers and arithmetic numbers. We know the overall length is x plus 0.8. And this is true, right? Because x has a value, we just don't know it. So we use that. We use that x, and we say, well, the whole length of this is x plus 0.8, regardless of what x equals. And this is an algebraic expression, because until we physically measure this piece, we don't know its value. But here's the nice thing about algebra is you don't need all the information to have a final answer. If I said to you, I gave you this diagram and I said, okay, what is the length of this part? And this is all of the information I gave you right here. What is the length of this part? The final answer is x plus 0.8. That is the final answer. And that's something we have to get used to now in algebra. We're used to having a final answer be a number we recognize, an arithmetic number. But in algebra, it can be a combination. Another good example of that is if you were to have this piece of bar stock, we had a hole here, a hole here, a hole here, one here, and one here. And I said to you that, get my crosshairs in here real quick. I said to you that the distance from here to here is a long. And the distance between the center of this hole and the center of this hole is b long. And the distance between the center of this hole and the center of this hole is also b long. The distance between these two centers is c long. And between here, this center and this center is d long. And this is a long. So if this was the question I gave you, or the problem I gave you, and I said, okay, what is the total length of this part? You know, the way we've been trained in school is we look for numbers. These letters are numbers. They are literal numbers. So we can answer this without having an arithmetic number attached. So the answer to this is 2a, right? 2 times a, there's two of them, right? So you could say a plus a, but this is the more correct way of doing it. Okay, so 2 times a plus 2b plus c plus d. That's the answer. In algebra, that's what we expect will be the answer. One of the ways you may see this in industry is you may be creating a part. Maybe you make tens of thousands of this part, but depending on the customer, the location of D and the location of B is different. Or maybe a company makes 20 different versions of some part, and in each version, the distance of one of these values is different. So having a common print like this, where A is always A, right? The distance from the ends is always A. The distance between the first two holes are always B. The distance between the middle two holes is always C, and the distance between these two holes is always D. Even though these values change, you may be in a situation where the product itself, the location of everything, or the size of everything is the same, but the location changes depending on the application. So this is where algebra applies, is that these are the knowns, but the values are dependent on the product, right? So in one application, A may equal 4. In another application, A may equal 3. So obviously, when we add up all of the values, the arithmetic values, the overall length is going to change. And the distance between holes will change, but the general look of this product is always the same. So this is another thing we look for, is this. If we have literal numbers given to us, have we also been given an arithmetic value to those numbers? So before I give you an example of that, I want to make sure I stay on track with our walkthrough here.
Question.
Yeah, go
What's the
ahead.
practical application of adding letters in there? You like industry kind
Right.
of thing? You know what I mean?
Yeah, so that's a
I
good
mean, I
question.
can see if like A is always 4. and then, you know, you put in like 3 or 4 different A's, that kind of makes sense, but
Right. Well, let's say, for
seems like they just
instance,
want to put in letters for fun.
yeah, 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 and you know, I appreciate that because a lot of times we'll look at math that we're learning and say, why do I need this, right? So try to imagine, like, for instance, if we had worked in a shop where we drill a lot of holes for parts, like we have um, what do you call that? Like drill, like gantry drills, you know, multiple drill heads all set up at the same time to all produce holes. Well, all of those gantries, all those heads of those drills can slide along a slide, right? So that you can reposition the heads wherever they need to be to create the holes below. So if you have a product that you make, let's say it's plates, right? That are support plates for the mold industry or aerospace, and those plates, depending on the customer who's buying those plates, although all the plates are the same size, let's say the outside dimensions are all the same, customer A puts all of his holes in this location, and customer B puts all of his holes in this location, right? Customer C, customer D, blah, 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 blah. So you, to generate prints, blueprints, or engineered drawings for every single one of these components may be counterproductive. It may be just more productive to say, okay, so here's our generic. I don't know why this won't erase, but here's our generic print. Okay, and the location of these holes will be based on the customer. So customer A, right? Customer A, all of his holes are at 3 inches and 3 inches. Customer B, all of his holes are at 2 inches and 2 inches. C is at 1.7 and 1.7. So all the customers want the same part, but they all want their own little twist on. You know, this is why things cost when you go get your Honda fixed as opposed to your Ford, why it costs more, right? Because of the custom parts, custom bolts, blah, blah, blah. So have one print and just say that we shouldn't call this customer A, but regardless, let's just say feature A, B, and C. So this is customer 1, customer 2, and customer 3. Okay, so customer 1, we know anytime that we manufacture their parts, all of the A dimensions, we would look to a chart. Look over here, what's the dimension of A? Oh, it's 3 inches in X, and it's 3 inches in Y. Right? So that's where algebra would be helpful. Like right now, it's just saying the distance from the edge of the part to the center of the hole for customer 1 is A. So we look over here, oh, A has an arithmetic value. It's 3. So this is algebra doesn't have to be about trying to solve unknowns. It can be used in referencing as well, right? So customer B, the value, you know, their the location of their holes is 2, and customer C is 1.7, 1.7. There's always applications. Otherwise, it would be completely pointless. I will give you one that you'll like here. Let's see if I can find the one I used last time. So here's one that you'll like. So imagine, I don't know if you guys have ever seen like a gang mill, but basically on a horizontal mill.
Gang something?
What's that?
You say gang mill?
Yeah, gang mill. So on a horizontal mill, right? The cutter doesn't. So you don't have a vertical spindle. You have a horizontal spindle. And on that spindle, you can put an arbor, and on that arbor, you can put several cutters, right? So you essentially get, let's say, a cutter that's here, right? And then you have another cutter that's here, and you have another one that's here, just to kind of give you a little bit of a, I know my drawings are kind of horrible, but you'll get you get the point here. A cutter here, and then another cutter here. Okay, so you can stack up your cutters, right? So they all sit on an arbor like this. So these are all cutting edges. Right? These are all cutting edges.
A gang of cutters.
Yeah, so you literally gang up all of your cutters, right? And you put them beside each other. And then when you bring this cutting tool into the part, you create the shape, right? You create the shape of the ganged up tools. So as these plunge into the part, you end up with this shape. Now, the width of these slots, let's just say, for instance, that all of this whole length of the part, and let's say the length of this, this, and this are always the same, always. But the length of this, depending on the company, the customer, the part, this changes. So this is the unknown. This is A. So we may know that, and then let's just say that this is always the same. So this may always be 1 inch. This may always be 2. This may always be 2. This may always be 3, 2, and 4. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14. So the overall length of this part is always going to be, let's say, yeah, it'd be 14 plus A. Okay, so what that means is the overall length of this part can fluctuate. It won't always be the same overall length. It will fluctuate. So this we'll say that this is the feature that matters. So customer 1 only wants this 2.5 inches wide. So the overall length of the full part when finished is going to be 16.5 inches. Right? Customer 2 wants this 6 inches wide. So the overall length is going to be 20 inches. So this is where algebra matters, because you would gather up all of the like numbers. So all of the arithmetic numbers, 1 plus 2 plus 2 plus
add them with the variable.
3. Right. Okay. Plus 4. Wait, 1 plus 2 plus 2 plus 3 plus 2 plus 4. Right. So let's, and that's plus A. And then you would say equals 14 plus A. Right? Because we don't know what A is. So this is your answer. Your answer is 14 plus A. This is the variable. This is the literal number that could change. Right?
So that's why you use a letter then.
Right, because although it has a value, we just don't know what that is. And it can change, right, depending on the application. So, you know, I can totally appreciate, you know, going through something like this and saying, you know, what's the value here? How does this benefit me? But if we know how to manipulate the literal numbers and arithmetic numbers to, you know how we're always talking about solve for the unknown? In arithmetic, that's what we're doing. We try to gather up all the information we can and only leave or isolate the unknown. Let's just do a couple of things I need to cover with you guys so that we can do this properly. I know you guys have done this, but it's a good reminder. Bed mass. Now, when I sent you the lesson plan for tonight, I outlined bed mass, and one of the things that's important, and keep this somewhere, so if you forget, you have something to reference. This means that in any algebraic expression, let's just pick one. I'm going to write down 3x, and then we'll talk about how to do this. 3x minus 2y plus xy. Okay, we need to understand what we're looking at. Now, maybe just before I talk about BEDMAS, one of the things that we do have to acknowledge, and I put this in the lesson plan so you can refer to it. And when you guys are doing your assignment, look back to this lesson plan, because you can't afford to forget this. The letter X, we talked this a couple weeks ago. We use x extensively in algebra. Therefore, we don't use multiplication symbol anymore. This is obsolete. When you see x in an algebraic expression, it means it's a literal number. It's not 3 times minus 2. The x is a literal number. It's part of the alphabet. We no longer use the multiplication symbol. What we do is we use parentheses to identify multiplication, or we don't put a symbol at all. So here's an example. In the xy, notice this says 3x. That means 3 times x minus 2 times y plus x times y. So if there is no symbol between two literal numbers or an arithmetic number and a literal number, then it's multiplication. Now, that's not true about arithmetic numbers, right? If I see a 3 and a 2 beside each other, that's 32, right? It's not 3 times 2. If this was 3 times 2, then you would write it 3 times 2. So please, when you're multiplying and your answer includes multiplication, instead of putting 3 times 2, put 3 times 2 by using brackets, okay? Just imagine the multiplication system no longer exists. Okay, not the multiplication sign, sorry, no longer exists. You have to use brackets. So what we'll do is we're going to just show you how this works. Okay, so I'm frozen. Are you guys still there?
Yeah,
Yep.
I'm still here at least.
I keep freezing up, so I'm going to try and keep this short and sweet. All right, let's go back to this question here, 3x minus 2y plus xy. Okay, BEDMAS states this, that the very first thing you do is brackets. That's what the B stands for. So anything in brackets, I don't see anything in brackets, so we don't have to worry about it. The very next thing that we do is exponents, and by extension, we also would do the square root, right? Square root is the opposite of exponents. So brackets come first when solving an equation. Second comes exponents. Okay. Third is division and multiplication as they appear. In other words, if this was divided by 3, we would do division and multiplication as they appear. So I would do multiplication and then division, multiplication, multiplication, right? I don't have to do all of the multiplication and then all of the division. You do them as they show up, right? So if it happens to be 4 divided by 3 times x, right, you would do your division first because it shows up first. If division showed up at the end, right, divided by 12, okay, you would do multiplication, 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 then division. So you do them in the order they appear, right? That's the division and multiplication. The same with addition and subtraction, right? Addition and subtraction as they appear. Okay, so as you come across addition, you do the addition. Subtraction, you do the subtraction. Okay, so let's just use this example and do this together. In our example question, x has a value of 12 and y has a value of 6. So now we'll rewrite our equation here and include the arithmetic numbers. So 3 times x means 3 times 12. So the first thing we do is any information that we can add into our equation, we do that first before solving it. So if x is 12 and y is 6, let's add that into our algebraic expression. So minus 2 times 6 plus 12 times 6. Right? So let's make sure we got everything. I have an x here, I put a 12 here. I have a y, I put a 6. I have an x, I put a 12, and a y is a 6. Now, remember multiplication comes first, right? So there won't be any accident happening with adding this 12 and then multiplying by 6. Now we do the multiplication and division as they appear, and then we do the addition and subtraction, right?
96.
So let's go through it, right? 3 times 12 is 36, minus 2 times 6 is 12, plus 12 times 6 is
72.
72. Thank you. Okay, so we did our multiplication. Now we do our adding and subtracting as they appear. So 36 minus 12 is 24 plus 72. And therefore our answer is 96. Okay, and this is why BEDMAS is so important, because if you did this in any other order, you're not going to get the right answer, right? So think of BEDMAS. This is your rule, right? To solve algebra, that's your rules. That's the rules. Follow the rules. And we'll do one more example of some basic algebra here. I showed you in your lesson plan that parentheses are brackets, right? It's the same thing. So we typically call them parentheses, but parentheses are brackets. So you do all of your brackets first. So if you came into a situation, let me ask you, 2.134 minus 1 divided by 4.5 plus 6.1. In algebra, where would your mind go first? What are we told to do first? Brackets, right? We don't have any brackets. What's next? Exponents. We don't have any exponents. What's next? Multiplication and division as they appear. Now this is where logic in mathematics comes in. Okay, it's the rule in BEDMAS says that I divide first, but you cannot divide a numerator by a denominator if the numbers are not whole numbers. So therefore, when you have a situation where you need to divide, like when you come across a fraction like this, you can't solve it unless you're dealing with actual numbers, whole numbers, right? So what you would do in each and every case is you would put brackets, your own brackets, around the numerator and around the denominator. Because what this does is it goes back to what is it that we're trying to solve. When we're trying to solve a fraction, we want to know how much is this of this. That's the logic, right? How in a fraction, this divided by this. Go back to pies. Well, first of all, I have to know, well, how much is this? How much is the numerator? I can't figure out how much it is of the denominator until I actually know what the numerator is. So anytime you have unsolved arithmetic numbers as a numerator or denominator, put brackets around them to solve them first. That doesn't mean that you're going to always be manipulating algebraic expressions to make them be what you want. That just means that in math, you can't divide a numerator by a denominator unless you know what they are. And so to do that, you have to put brackets around them. So think of it this way. There are always brackets around a numerator and a denominator. Okay, so in this case, we would solve that first. It would be 1.134 divided by 10.7. So now we can solve this, right? We can divide 1.134 by 10.7 and we can get an answer. So if you come across this, and you will, if you come across numerators that you have to add and subtract numbers to get a numerator, put brackets around it and solve it. And you got to do that with the denominator. Do the same thing. You got to have whole arithmetic numbers to complete a fraction. Okay. So you may want to look back at this section on YouTube once this is uploaded. Okay, one last thing. Double sets of brackets. Okay, so if we had an expression like this, 4 plus 15 minus 3 times 2 minus 3. So yeah, if you've ever wondered, well, how come I have 2 sets of brackets on my calculator on my keyboard? Well, this is the reason why. Brackets within brackets. Can you imagine if you had multiple questions where it was like 4 plus 3 plus 2 minus 6 times 4 minus 2 times 3, right? You start seeing all that, you're like, oh my Lord, what am I looking at? We have 2 sets of brackets, right, that we can use. So we can use them interchangeably so that we know what we're working inside of. Whatever the bracket is on the left side should be the same bracket on the right side. And you're going to come across long strings of algebraic expressions that are long strings that, you know, there's no sense trying to solve it if you don't know what you're looking at. So keep it simple. We have 2 sets of brackets for a reason. How do we work this? What do we actually do to solve an equation that has multiple sets of brackets? Find the innermost brackets and solve them first, right? So in this case, we would solve everything inside of this bracket. So let's focus our attention on this for a second. How do we actually solve this? I get in the habit of rewriting the entire formulas and then only solving what I need. So right now my focus is on this. I'm not worried about this stuff yet. So 15 minus 3 times 2. Go back to BEDMAS. I'm inside of my brackets, but the rest of BEDMAS still applies. I'm doing the brackets first. Do I do 15 minus 3 or 3 times 2? Well, what's after brackets? Multiplication and division as they appear. So it'll be 15 minus, what's this? 3 times 2 is 6. So I'm working inside of my brackets, and then I look for exponents, don't have any. Division, I don't have any, but I do have multiplication, so I do that next. And this is how my equation looks. And I will rewrite this, even now. I don't skip ahead. I rewrite my equations step by step by step. That way, if I make a mistake, I can look back and say, oh, you bonehead, that was the error. Now, notice I still have brackets. So I will rewrite this 4 plus. Now I work inside of my brackets. 15 minus 6 is 9 minus 3. And now I'm only working inside of one set of brackets, which I don't even need them now because it's just addition and subtraction, but they're there. I apply them. 4 plus 9 minus 3, so is 10, right? So that's how you would work your way through using BEDMAS. I don't know, would one of you guys just try? Oh, okay, sorry. Okay, I hope that makes sense. So before I break this off and let you guys get your assignment, I want to just do a couple of quick examples of a little bit more complex calculations, okay? So let's do an example. And so what I'm going to do is I'm going to draw this one out, write this one up. I want you to take, I'll give you a couple of minutes just to see if you can rewrite the next step, okay? And then I'll ask somebody to share that. So I'm going to put up, let's see, let's do this one. So I'm going to say that m equals 5, p equals 4, and r equals 3. And here's your question. M plus MP squared minus R squared. Okay, so what I want you to do is go to the next step, right? So that, remembering that we have arithmetic values attached. So rewrite this according to the values. So I'll give you 631, 630, I'll give you to 632, and then I'll ask somebody to tell me what that next step is.
Well, you saying solve it or just write it?
No, just write the next line. So like I did in the last example, right? So replace the literal numbers with the arithmetic numbers and tell me, including your brackets, what the next line would be. We'll do that together and then we'll do the next one. All right, so who wants to take a stab at it? How would I rewrite the next line? And I'll follow what you say. Who wants to jump in?
I'll give it a go.
Who's that?
It's Josh.
Okay, Josh, go ahead.
Okay. So do you want me to replace the letters with the corresponding numbers?
You got it.
Okay. So 5 plus left bracket m, left bracket p, right bracket, and another right bracket, I guess. And
Okay.
then the
All right. I'll do what you're saying, and then I'll correct it if it needs it.
Okay, minus 3, 2. Or sorry, I meant to
Okay.
say the instead of the letters, the numbers. So 5, and be in the brackets. I got confused with the brackets.
That's okay. I'm gonna just fix that. Okay. So you want 5 here.
Yep.
4 here. Okay.
And then minus r squared.
3
R3
squared. Okay. All right. So one of the first things I'm going to put. Thanks, Josh. Appreciate that. So one of the first things I want to point out is what the exponent belongs to. Okay. So would this work on a calculator? You probably get the same result. The more right way to write this for simplification would be 5 plus 5 times 4 squared. Now, why that is because remember that this isn't one number. This is 5 and this is 4, and they're multiplied together, and it's the 4 that has the exponent attached to it. And because exponents come first, we need to know that, like for instance, if this exponent applied to the m and the p, then they would be in brackets, because that would mean that you'd have to multiply them and then do the exponent too, right? So because there's no brackets around the M and the P, and I just put them there, then I'm just going to undo that and undo that. Because there's no brackets around there, that tells me that this exponent only belongs to the P, okay? So I would write that way, right? 5 plus 5 times 4 squared, right? And then minus 3 squared. So the difference here being that in this case, you're multiplying 5 times 4 because brackets happen first, and then you're doing the square root. This would give you the wrong answer. But so this is the part I want you to really try and grasp here. The exponent, remember, brackets and then exponents. Brackets come first. Are there any brackets here? There are not any brackets here, so exponents come first. So you have to look at this and say, where does the exponent belong? It belongs to the P. How do I know that it belongs to P? How come it doesn't belong to the M and the P? Because if it did, this would have brackets around it because this would apply to both. Okay, so when you see an exponent on a literal number or an arithmetic number, it belongs to that number. Okay, it will only belong to like the M and P or any other combination of literal numbers if they're solved first. Okay, so this would be the right way to write this, and I appreciate, Josh, you jumping in and not being afraid to get it right or wrong. So now we can solve this, right? So we look back to BEDMAS. What's the next step? Well, brackets is the next step. We created the brackets because it's 5 times 4 squared. It's still the right thing, right? So this is a 5. We know it's going to be times this 4 because there's no symbol in between. And we know the exponent belongs to the 4. So we have to do the exponent first. So 5 plus 5. 4 times 4 is 16. Minus 3 times 3 is 9. So you can do the exponents at the same time, right? You can do all the exponents in a row. So now I've solved this exponent, Now I can do 5 plus whatever 5 times 16 is. I guess I should have thought about that first. Okay, so 80. 5 plus 80 minus 9. So 85 minus 9 equals 76. Okay, and I know this looks like a lot of work, but I'm going to tell you, if you do it this way, no matter how many lines this takes, when you get something wrong, because eventually you will, you can look back and say, okay, where did I mess up, right? Or was it just a transfer error? You know, I wrote it wrong. You'll see with the assignment that you're going to get tonight that some of the marks are higher. A lot of them are marked out of 4 because you have to take this information, the arithmetic values of the literal numbers, and you have to plug them in. So I give you marks for plugging them in the right place. And then I give you marks for answering it correctly. So I don't really give you marks for all this, but if I see that you plugged all the numbers in right, but you have the wrong answer, I can at least find where you messed up. And if I just see that, you know, you came down here and you just forgot to write the 9, I'll make a note there, right? And say, I won't mark it wrong. I'll just make a note and say, hey, there's a transfer error. Just make sure you write everything down. It's not showing that you don't understand it. It's just an error that you made in transferring. So I always write out everything, so that I can look back and make sure I covered my bases. Okay. So make sure I covered anything that you guys are going to see. Here, we're going to end on this note. Please follow this rule. In principles of geometry, I said to you guys, you don't have to memorize the principles, but know what they do. So be familiar with what the principles allow you to do, or what the principles tell you you have to do to solve geometric questions and equations. BEDMAS is the same with algebra. This is the rule. This is it. So apply this to everything. There are